Alright, today we are going to complete the exponential growth and decay video 1. The target for this video is I can find a growth and decay rate and factor and use them to create tables, graphs, and equations for exponential functions. So the first example that I have is about a fish species. It says a different fish species triples in population annually. If the fish population starts at 35 fish, create a table and graph and show the growth that shows the growth over time. So if our fish population triples, that means each time we're going to multiply by 3 for every year. So if I take, to create the table, if I take 35 times 3, that'll give me the fish population after 1 year, which is 105. Then if I take 105 times 3 to triple that population for the second year, I get 315. And I continue that pattern. Times 3 will be 945. Times 4 will be 2,835. Sorry, times 3 will be 2,835, and times another 3 will be 8,505. So to get each value, we just multiply the previous one times 3. Now I need to graph that, so I need to label my x-axis as years, my y as population. So my years go up by 1, so 0, 1, 2, 3, 4, 5. Now my fish population doesn't go up by a constant rate of change, so I need to know how much I need to go up by to represent up to 8,505. To do that, I'm going to take 8,505 and divide it by how many spaces I have. 1, 2, 3, 4, 5. When I do that, I get approximately about 1,700 and so. So I'm going to round that up to 2,000. So this will be 2,000, 4,000, 6,000, 8,000, 10,000 is a good scale to go by on the y's. Remember, your scales have to be a constant rate of change. This space can't represent different values. It always has to be the same value. In our case, this space here on the y-axis is 2,000 fish. On the x-axis, each space represents 1 year. Now I'm ready to plot my points, 0 and 35, and I'm just estimating these. 1 and 105, 2 and 315, 4 and 945, sorry, 3 and 945, 4 and 2,835, and 5 and 8,505. So you can see that it has that exponential curve where it starts off growing slowly and then rapidly increases by that multiple of 3. The growth factor is what we multiply by in the table. So in this case, the growth factor is 3. And the y-intercept is our starting value, how many fish we started with, and in this case it is 35. So growth factor, what we multiply by, and the y-intercept is our starting value. Now it asks us, oh, I'm sorry you couldn't see that. Let me pull it up there again. So growth factor is what we multiply by, and that is 3. Y-intercept equals 35, and that is our starting value. So the third question says, what is the equation that represents this relationship? And the equation for exponential is always y equals a times b to the x, where a is the starting value, and b is the growth factor. So our equation is y equals 35 fish to start with. We grow by tripling, which is multiplying by 3 to the x power. Alright, so there's your example of exponential growth. Your second example is of exponential decay. And this one says a forest covers approximately 1,000 square miles. Every year, 10% of the forest is removed for development. Create a table and graph this relationship. Alright, so they tell us that our starting value is 1,000 square feet. So at 0 year, our forest coverage is 1,000 square feet. Each year, the forest decreases by 10%. That 10% is called our decay rate, how much we're decreasing by. When we have to continue our table, we can't use our decay rate, we have to use our decay factor. And to do that, we're going to say how much of the forest is left after this 10% goes away. So if I take 100 minus 10%, that leaves me with 90% of the forest stays each year. But we don't multiply by percent, so we have to change that percent to the decimal, so our decay factor will be 0.9. So that means every year we're going to multiply by 0.9 to get how much forest we have left. So at year 1, 2, 3, 4, 5, 6, 7, 8, we're going to go up to 8 years. So to find after 1 year, we're going to take 1,000 times 0.9, which gives us 900. Then to find after 2 years, we'll take 900 times 0.9, and that'll give us 810. Then we'll take 810 times 0.9, 729, and keep continuing that pattern. After 4 years, it'll be 656.1, 590.49, 531.441, 478.2969, 430.46721. Alright, now I need to graph that relationship. So my x-axis is my years, my y-axis is forest coverage. Years are going by 1, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We got some extras. So we have 10 spaces here, and we have to represent up to 1,000. So I'm going to take 1,000 divided by 10, and that gives me a scale of 100. So 1,000 divided by 10 gives me a scale of 100. So each space on the y-axis is going to go up by 100. So this will be 100, 200, 300, 400, 500, 600, 700, 800, 900, and 1,000. So I plot my points. 0 and 1,000, all the way up here. 1 and 900, 2 and 810, 3 and 729, 4 and 656, 5 and 590, 6 and 530, 7 and 478, 8 and 430. So you can see it's decreasing slowly at that exponential rate because we're only decreasing by that 10%, but it still has that curve going on. You can see if I put a straight edge there that it's not linear because here these 2 points connect like that. So you can see that curve. It is very slight, but it is still that exponential curve. Alright, so we got the table and we got the graph. Now it asks us to answer these 3 questions. What is the decay rate of the relationship? And remember, the decay rate is that percent that we're decreasing by. That is 10%. The decay factor is what we multiply by each time, and that was the 0.9. So when we write the equation, it's in the form of y equals a times b to the x. So y equals our starting value, which is 1,000 square feet of the forest, times our growth factor, which is 0.9 to the x power. All right, final problem that I have for tonight. Where did my copy go? Oh no. The final problem that I have for tonight, I already have it worked out for you, so I'll talk it through. It says the decay factor, decay rate. It says boiling water is 100 degrees Celsius. It's put outside to cool off. The water cools off at an exponential rate. After 1 minute, the temperature is taken and the water is 85 degrees Celsius. What percent did the temperature decrease by? Well, if we started at 100%, 100 degrees Celsius, and we subtracted the 85 that it was after a minute, we're left with 15. And since we started at 100, we can just make that a percent. It's 15%. So our decay rate is 15%. So our water is losing 15% of its heat after each minute. So fill in the table assuming the temperature of the water continues to decrease at the same rate. So this decay rate, we now need to switch into the decay factor. Well, the decay factor is what's left over. So 15% of the heat is going away, but 85% of the heat is staying. So we got to change that 85% to a decimal, which is 0.85. So there's our decay factor. So to complete our table, we're going to multiply each term by 0.85. So 100 times 0.85 is 85. 85 times 0.85 is 72.25. And so on down the table, multiplying each one by 0.85. So now the question says, what is the decay rate? What percentage did the temperature decrease by? And we talked about that at the beginning of the problem. That is 15%. What is the decay factor? What was the previous value multiplied by to find the value? That was 0.85. We multiplied each value in the table by 0.85 to continue our pattern. How does the decay rate compare to the decay factor? The decay rate is the percent you decrease by, and it is expressed as a percent. The decay factor is what you keep and is expressed as a decimal. It is also what you multiply by in the table to find the next value. So finally, we want to write the equation of the relationship between time and temperature. So that's y equals, we started at 100 degrees Celsius, and our decay factor is 0.85 to the x power. So y equals 100 times 0.85 to the x power is our equation. Thank you guys. Hope we reached our target, and we'll look forward to doing more problems when we get into class tomorrow.